We now start the presentations of the last module, module 5 of chapter 9. Now, in this module, we are going to concentrate on a particular property of the measure. Now, recall that when we had studied Lebesgue outer measure and Lebesgue measure, it had this particular property that whenever a set A of real numbers has Lebesgue outer measure 0, then any subset B of A also had Lebesgue outer measure 0. In other words, whenever I have a set A of real numbers which has Lebesgue outer measure 0 and so is measurable, all its subsets are also measurable. But in general, an abstract measure mu does not have this property. So, in this module, we are going to introduce the notion of complete measure, the measures which have this particular property. So, let us see the formal definition of a complete measure in the first slide. We now give the formal definition of a complete measure. A measure mu defined on a sigma ring S is called complete if whenever we take a member of S E whose measure is 0, all its subsets also belong to the sigma ring S. Note that if mu star is an outer measure defined on a hereditary sigma ring H, then the measure induced by it on the sigma ring of all mu star measurable sets has this property, and we have already mentioned that the Lebesgue measure has this property, that is Lebesgue measure is a complete measure. But in general, there are examples of abstract measures which are not complete. If mu is a complete measure on a sigma ring S, then evidently all sets of the form A delta n belongs to S, where A belongs to S and n is a subset of a member of S of measure 0. So, as we have mentioned that in general a measure defined on an arbitrary sigma ring may not be complete, but using the above mentioned fact, we can actually extend any measure to a complete measure. So, this is our main theorem in this module. Let mu be a measure defined on a sigma ring S. Let S star be the collection of all sets of the form A delta n, delta stands for the symmetric difference, where A belongs to S and n is a subset of a member of S which has measure 0. Then we first show that S star is a sigma ring, then we show that the set function nu defined on S star by nu of A delta n equal to mu of A, this is a complete measure. We start the proof. First, note that if we take any two sets of that particular form A1 delta N1 and A2 delta N2, then their symmetric difference can be written as the symmetric difference of A1 delta A2 and N1 delta N2. Note that since A1 A2 belongs to S, so A1 delta A2 belongs to S and N1 and N2 are both subsets of a set with measure 0. So, N1 delta N2 also is a subset of a set with measure 0. This shows that S star is closed under symmetric difference. Again, if we consider the intersection of two such members, A1 delta N1 intersection A2 delta N2, we can write it as A1 intersection A2 delta A1 intersection N2 delta N1 intersection A2 delta N1 intersection N2. Now, all the three sets on the right hand side after A1 intersection A2 are subsets of some set of measure 0, and so combining them we can write it as just n. So, this set is of the form A1 intersection A2 delta n, where the set n is evidently a subset of N1 union N2, and so is a subset of a member of S which has measure 0. So, this shows that S star contains finite intersections also. So, we have shown that S star is closed under finite intersections and symmetric difference. Since we know that for any two sets A and B, A union B can be written in this form, that A delta B delta A intersection B. So, it follows that S star is also closed under finite union. Again, S star actually contains the differences also, which follows from the well known identity that we can write A minus B as A intersection A delta B. So, we have already shown that S star is a ring. Now, we are going to show that S star is a sigma ring, that is, it is closed under countable union. So, for this, first we note that for any A belonging to S and E belonging to S, for which mu E is equal to 0 and n is subset of E, we have the following identities. A delta n can be written as A minus E union A intersection E minus n union n minus A, and A union n can be written as A union E delta E minus A minus n. So, this shows that instead of writing the members of S star as A delta n, we can also write them as A union n, where A belongs to S and n is a subset of a member of S of measure 0. Now, it is easy to observe that for any countable number of members A k union N k, k belonging to capital N from A star, the whole union A k union N k, which can be written as union k equal to 1 to infinity A k union k equal to 1 to infinity N k, and this shows that the union is also of the same form, and this proves our assertion that A star is a sigma ring. Now, we go to the proof of the second assertion. For that, we first want to show that the set function nu is well defined. Suppose a member B of A star can be written in two ways, like B equal to A1 delta N1, which is again equal to A2 delta N2. Note that then A1 delta A2 is equal to N1 delta N2, where the set N1 delta N2 is obviously contained in a set in S of measure 0. Then A1 delta A2 is also contained in a set of measure 0, and we have mu of A1 delta A2 equal to 0. But then we have mu A1 equal to mu of A1 intersection A2 equal to mu A2, and consequently nu of A1 delta N1, which is defined as mu A1, which is equal to mu A2, and this is the value of nu of A2 delta N2. So, this shows that the function nu is well defined. In order to prove that nu is a measure, we only have to show that it is countably additive, because in any case it is taking the values of mu, and mu being a measure is already non-negative, and mu phi is equal to 0. So, let us start with a sequence of pairwise disjoint sets B k, k belonging to capital N from S star. As we have observed, we can write B k as A k union N k, where A k belongs to S and N k is a subset of a set of measure 0. Note that the sequence A k is also pairwise disjoint, and by countable additivity of mu, we get nu of union k equal to 1 to infinity B k. This is equal to nu of union k equal to 1 to infinity A k union k equal to 1 to infinity N k, and this is equal to, by definition of nu, mu of union k equal to 1 to infinity A k, but since mu is a measure and so is countably additive, this is equal to sigma k equal to 1 to infinity mu of A k, and which is equal to sigma k equal to 1 to infinity nu of B k. So, we have shown the countable additivity for a mutually disjoint sequence of sets, and we can show it for any countable collection of sets as we have done many times before. Finally, we want to show that the resulting measure nu is complete. So, we start with a member C of S star such that nu of C is equal to 0. Since C is of the form A union N, where A belongs to S and mu A is equal to nu C, this follows from the definition of nu, and N is a subset of a set from S of measure 0. So, it readily follows that C and all its subsets are again subsets of a member of S whose measure is 0. And noting that phi belongs to S, it is evident that all the members of C belong to S star. So, this proves that nu is a complete measure on S star. And this particular measure nu, which we obtained by this particular manner, this is called the completion of the measure mu. We can also prove another interesting result, which shows that if mu is a measure on a sigma ring S and mu star is the induced outer measure on H S, then every B belonging to S star, where S star is the collection of those sets which we defined in the last theorem, they are mu star measurable and mu star B is equal to nu B. We now present the final result of this module. If mu is a sigma finite measure on a sigma ring S and mu star is the induced outer measure on H S, then the collection S star again, which was described in theorem 9, this coincides with the class S bar of all mu star measurable sets, and moreover the restriction of mu star on S star is actually the completion measure nu of the measure mu. From the above lemma, we already know that S star is subset of S bar. To prove the converse, recall that if the original measure mu is sigma finite, then the induced outer measure mu star is also sigma finite. Consequently, for any member C belonging to S bar, we can find a measurable cover D belonging to S of the set C, where evidently mu star of D minus C is equal to 0. Again, if we apply the same result on measurable cover to the set D minus C, we can get another measurable cover F of D minus C coming from S, such that mu of F is equal to mu star of D minus C, which is equal to 0. Now, clearly d minus c can be written as phi delta d minus c, where phi belongs to S and so d minus c belongs to S star. Note that we can write c as d minus c. Since S is subset of S star and S star is already closed under difference, so we get C belongs to S star, and this completes the proof. So, to summarize, what we have done in this module is that we have defined the notion of complete measure. A measure mu defined on a sigma ring S is called complete if for any member E coming from S which has measure 0, all its subsets also belong to S. We already have examples of complete measures like the Lebesgue measure, like any measure which is the restriction of an outer measure on the class of measurable sets, but in general it is not true that any measure defined on a sigma ring is complete. And we have also presented a method to get a complete measure from a given measure, which is called the completion of that particular measure. And with this we finish this module.